20 spools.
Wow, that was crazy.
Yeah, well, he's actually started recording.
I'm glad you're doing something that you like.
Yeah, he started recording, so we have to behave now.
Exactly. Oh, he did?
Well, I didn't think. I forgot that it was going to start immediately.
Yeah,
we got 4 minutes early.
Exactly.
Yeah, and Tim Campbell will be joining us as well.
I forgot that it was going to start immediately.
Oh, perfect. Yeah.
We got 4 minutes early.
Oh, someone has got YouTube open in the background.
I forgot that it was going to start immediately.
Oh, perfect. Yeah.
We got 4 minutes
Close it
early.
down. Ooh. Yeah, you get audio feedback if you have YouTube open at the same time. I do a lot of streaming. So
yeah, there we go.
So yeah, currently this is what I'm imaging.
Oh, a sunspot.
Oh, it was crazy just minutes ago. Look at that. There you go.
I hope we get members of the public in here. Like
Look at
non-club
that.
members.
That was
Oh, it was very active.
Well, we've got some concurrent viewers on YouTube, so.
Okay, cool. I'm going to join the YouTube because I want to. Are you going to read out the questions, Jeff, or what?
I don't have any questions to read out, but I can basically keep an eye on the chats.
That's what I mean. Yeah, we like the other
side.
general questions about what's going on is explaining the science about
Sure.
what happens on the sun. Tim and I will be all over that.
Okay.
So we nerd out on this kind of stuff. So
No.
you wouldn't have guessed a little bit, maybe. So we'll like Tim and I will cover that. Tim is might be a little bit later joining, but he will. He said he'll join.
Okay.
And then after that, then so you'll talk about what you're doing, about what you're looking at, and if people come up and have any questions in chat, Jeff, you can recite them out to us.
Yep.
I suppose we're getting ready to go live now, are we? Are we live already on YouTube?
Technically, we're live because I forgot I set the auto start.
Well,
so
let's give it a minute till the top of the hour, and then we'll do a quick intro.
yeah.
And
Well, that was the plan, but I wanted to see that the stream worked, and I forgot I set it on auto.
that's fine.
It's no big deal.
You can trim it out after the fact. You can go into YouTube and trim it out.
Yeah, for posterity. For right
Yeah,
now, they're just going to have to put up with our banter.
That's fine. We're not saying anything bad about anybody that we wouldn't say to their faces.
Well, right now, we can always edit that out, too.
Oh,
Then there's no fun.
look at those 2 new sunspots that are coming out.
Yeah. How much you magnified? Back off out of that image.
Well, let me stop.
You're doing a run. No, leave it if you're doing a run.
Let me stop recording.
No, let it run. Let it run.
So far I got, 300 and divided by 2. That's almost 150 videos.
Yeah, let me have a look at
But anyway, I'll go through this. That's basically what I wanted to do before everything else. So I could, compare solar activity within minutes or, hours.
Yeah, I'm just going to have a look at the sun as it is. So you're doing HA, correct?
Correct.
Okay, there is a couple of some activity, but not an
You're
awful lot.
talking about that?
So which sunspot are you on? You're on the one on the bottom
This
there,
one.
in the southern limb. Okay.
There's another one here.
Yeah.
Actually, there are correction.
There's 4 there right now.
There
There's some of them are
1, 2,
so small.
3, 4, 5.
Oh, 5. Okay.
So the one I'm imaging are actually 2 of them.
It looks like they're shrinking though. They're collapsing.
Yeah, is it?
Yeah, they've gotten small as far as I know. They've shrunk a little bit.
Why do I count 3?
There are 3 there. It depends on the atmosphere.
Yeah, true. Anyway, yeah, let me Do we have any viewers on YouTube?
We have 7.
7. Okay, Jeff, how about you do the intro? And then, yeah, you have to have something to do, right?
You mean I don't just set it and forget it? And
No, you don't get out that easy. Come on.
well, I'll wait till my officer badge wears out. Well, for those of you who are joining us, welcome to the, I guess this is going to be the first event of the 25th Astronomy at the Beach. You're in the H Alpha solar session, the 3 p.m. one, which is a little bit earlier than everybody else's, and it's being conducted by Awni Hafedh of the University Lowbrow Astronomers, and I think you probably belong to a couple others. Awni is one of our very finest astrophotographers and post-processors, so he's graciously agreed to show us all of his secrets today, as well as what's going on the sun. And we're joined by Liam Finn from the Ford Astronomy Club. And is that right, Ford Astronomy Society or Club? And he's going to help explain some of the sciences and other things involved. And together we're going to kind of field questions, and hopefully everybody can learn and kind of do an oh wow for this couple of hours here. So with that, I will let Awni begin.
Well, welcome everyone. My name is Awni Hafedh. I'm an amateur astrophotographer. I started on 2015 doing like minimum, small astrophotography with a small telescope, and things got in, I started getting advanced stuff and buying more telescopes, and, I still do it. It's just something that I have fun with. For this presentation or live view, I didn't know if the weather was going to be clear or not, so I had like plan A, plan B. Plan A was, setting up my telescope and do some live streaming. Plan B was preparing a presentation and explain everything about, solar imaging and explain everything about what equipment you guys need and what to expect and what difficulties that you might face with. And last and not least, how to get a decent image using solar imaging. So as a beginning, that's my name. And if you'd like to follow me on Facebook or Instagram, this is the link. And I'll go through the presentation later on, but would love to enjoy the clear weather that we currently have with some live view till some clouds or my southwestern tree covers my telescope. So let me just stop this. Yeah. So let's go with what I'm doing right now. I'm imaging the sun using a dedicated hydrogen alpha telescope. The way this thing looks like that. So I managed to take some screenshots. There you go. Hope that's readable and clear. So the scope itself is a Lunt THA pressure tuner. This is the guy. I have a Barlow through within the imaging tube. The Barlow makes the image, gives it more zoom, I would say, optical zoom. And this guy is a 2.5x optical zoom. The camera that I'm using is a dedicated mono camera. It's one of those ZWO 174 mono. And on top of that telescope, I made a 3D printer DIY device, or a plug that I can remote the focus and remote pressure tune from inside the house. I don't have to go outside and fiddle with the knobs. And everything else sits on a tracking mount, which is the iOptron CM25P. This is another look from the other side. That 3D printer pinwheel or pinions is basically to rotate the pressure tuner. The pressure tuner is very hard to rotate, so that's why that big gear here is to overcome the huge torque. And what else did I miss? Yep. So number 6 is, this is a USB hub. So everything here and here, the mount, the telescope, the remote focuser, the remote pressure tuner is connected to the hub. And the hub is connected to a 50-meter USB 3 extension cable that goes into this room. And last but not least, this is just mainly a power distribution box. Again, it's also DIY to run, to power up everything. So this is technically set up outside, and I'm connected through it. I'm connecting this computer to it through that 50-meter USB 3 hub. The way, what I use to run all my images is fire capture. I find this software very useful. It's very easy to operate, and it's filled with features, tons of features. And as we speak, this is the let's show what's going on the sun. So let me disable those features. And
so while you navigate there, so just so people know what a hydrogen alpha, for those who do not know what HA is, hydrogen alpha is the frequency of light emitted by excited hydrogen gas, and the sun is primarily hydrogen gas, because the sun operates from converting hydrogen, by fusing hydrogen into helium. Mm-hmm. And the frequency of hydrogen alpha is 656 nanometers. So when you have a telescope, this only allows that one frequency of light in. It allows you to see the prominences and so on the sun. Without that, you will not see those.
Brian Adams says, wow, it's a lot of technology. And do you ever trip on the cords, Awni?
Sometimes, yeah. From time to time, yes, I do. But it all matters about how to cable management. Cable management, whether it's a telescope, at night, at day, solar scope, anything. As long as your cable management is properly organized, and I can show you an example of what I mean here. There. Everything is inside a trunk, and the only thing that connects the telescope to my computer is just a single cable. That's it. So it makes, using such a cable management makes, you won't have any trouble with cables tangling between each other, or even during tracking, you don't have anything pulling the telescope or the camera off of its position.
The worst thing is if you trip and you over a cable and you pull the scope down. That's a lot of money. So
true.
You sacrifice yourself over the equipment.
Well, that's why you hide all the cables within within the path that you don't walk through.
Yeah. Well, and for the price of a couple of bucks of that trunk sleeving and all that, it saves thousands in damages. So
true. So let me show you some. So I'm controlling the mount from here, so I can slew the telescope and see what's going on the sun. So let me show you what the websites or what the experts show. So currently, as we speak, we have 1, 2, 3, 4, 5 sunspots. And so this can be, you can get those images every day updated from a website called spaceweatherlive.com. Now this is what you see if you use a non-hydrogen alpha telescope. You know, they call it a white filter telescope. Mainly it just dims, it mainly just dims the sun to a visual level that doesn't hurt the telescope or the camera or your eyes in this case.
Yeah, the white light blocks 99.9999% of the light.
Correct. So if you use that, and again, it's called a white filter.
White light, yeah.
White light filter. This is currently what you will see on the sun. You'll see those tiny dots, which are like they call it the sunspots. Now, if you use a hydrogen alpha filter, or no, I'm sorry, not hydrogen filter, hydrogen alpha telescope or eyepiece, and what you're gonna see is, hold on, where is it? There. So this is another website that shows you what's going on the sun through a hydrogen alpha emission. And if I click that, there you go. So currently we have the sunspot that what do you call it, 2872. Let's start with that. Oops. There. This is 2872. And over here, there are two sunspots. And apparently there's a sunspot here and a sunspot here. And you can kind of see it from all the uneven activity on the sun surface, like this one or this one. That's mostly a sunspot. So this is just website. That's technically what experts are telling you.
Let's explain what they're seeing here, if you don't mind. So if you look at the bottom image, the bottom of the image there around the sunspot, you see those black arcs that look like those black lines. So the sunspot is created by twists and knots in the magnetic field, right? Because they interact and it gets all twisted and knotted up.
Sure.
And that creates some of that activity. But as part of that, when the magnetic field gets so twisted and knotted up that it loops above the surface of the sun, it actually pulls up the super hot plasma from the sun into those arcs of magnetism, right? Those magnetic field arcs. And then inside that now, there's two names for the same for this entity. So what we're seeing here is called a filament because we're looking at it from above. We can't see its height. We can just see its shape from above, like a plan view, as if like in a building, right? Yep. But when it's along the edge of the limb, if you go over to the edge of the limb, you see the little prominences. Ani there, there's there, yeah. See those prominences? That's called a prominence. The prominence and the filament are the exact same thing. It's just that we've given different names based on our point of view.
Yeah, exactly. Yeah. So this filament or ejection, I would say, or plasma ejection, this dark filament, if it goes to the edge of the sun, what you're gonna see is that same filament visible through the edge. And it's not called filament anymore, it's called prominence.
Yeah.
So, but yeah, like Liam said, they're both the same.
Now, when those knots in magnetism break, and the plasma that's in there, when they snap and break, because they get so twisted up that they actually do snap and break, when that happens, they throw material off into space. That's what we call a CME, or a coronal mass ejection, or flare in the sun.
Sun flare, and technically that's what causes the aurora or northern lights.
Yeah, so a question I have and some others may is, once that happens, how long does it normally take before the aurora becomes visible on Earth once that ejection occurs?
About 3 days.
3 days.
So when the CME happens, coronal mass ejection, when the CME happens, it depends on where it happens related to us, because as the sun rotates, it leaves, if you imagine the sun is rotating like this, it leaves an arc of material that, as it casts off material, it branches out, and it leaves like an arc, a trail of material in space. And it takes about 3 days for that, at the speed it leaves, to reach us, roughly 3 days. Sometimes it's a little less. It varies on the force of the CME, but and depending on where we are, whether we get a blunt force hit with the main blast of it or not, will dictate whether or not we get aurora, because the amount of charged particles that reach us will dictate how much of an aurora we get, because those charged particles get pulled in by our magnetic field north and south. And as they come in, they excite the gas in the upper atmosphere. And by doing so, they make the gases glow, which is why we see aurora.
Yeah. A lot of it depends on how powerful the CME is.
Yes.
I used to work for the Center for Space Environment Modeling, and there are some outbursts that are powerful enough to reach us in as little as 9 hours to be affected by our satellites and things like that. The auroras are going to be obviously lagging behind because they're close in, but they've seen effects as little as 9 to 10 hours from ejection.
And they're really cool for people who are into amateur radio, because anyone into amateur radio, when we get hit with those charged particles, it ionizes their atmosphere. And anyone who's into amateur radio, you can actually bounce, when the atmosphere is ionized, you can bounce your ham radio, your amateur radio signal off the atmosphere and reach and actually receive and transmit signals further than you would when it's not ionized.
Correct.
That's cool.
So
yeah, we had an event where we had a lot of particles coming towards us, but Liam, like you were describing, it hit Earth, and it hit the magnetic field and got pulled away. Basically, it followed the magnetic field in such a way that the aurora wasn't as pronounced as we thought it would be because of how it hit the magnetic field. So it's like, instead of hitting it at a certain angle, it's like it got absorbed somehow, and it became
dispersed by our magnetic field. Our Van Allen belts can disperse it to some extent, but if it's strong enough, then it can get pulled in by the magnetic field north and south, and that's what excite the gases. Yeah.
Okay. Yeah. Those of us that are on Aurora watch were pretty disappointed when that happened. But one other quick question, then we let Awni continue, is there a particular reason that you all know or remember that aurora activity tends to be heavy around the equinoxes, the fall and the spring equinoxes?
I'm trying to remember.
I know there's a reason for it. It's something to do with our position in space and the fact that those are the days where we've got equal day and night. I thought there was aurora tend to happen, and we had clouds, but looking at looking at space weather, sure enough, their aurora would have been visible had there not been clouds in our area, to the north to the thumb of Michigan and north. We would have been able to see.
It's because of our angle. Remember, it's because our polar, our magnetic poles are at right angle to the solar wind. That's why we get them regularly at that time. That's why around the equinox is where you often see them. You can see them anytime, but that's a more prominent time. It's like a clock. You can almost set your watch to it most years, because our poles are at right angles to the solar wind.
Yeah. We got a question from Eric Southerly. So I've been hearing about a decent solar storm that is going to make the aurora very visible tonight. Do we know anything about that storm tonight?
Well, we got two. We got this guy here. That looks very promising, and there's another sunspot in another active region, which is facing Earth as well, which is this guy. So, and according to the website, there you go. We've got this guy and that guy.
Yeah, but I don't know. I didn't hear about that one. Let me check what the KP index forecast is. Okay, right now the KP for the next 24 hours, the index is at 3. So you need to be way up in the North Pole to be up around by the North Pole to see it. To be able to see aurora in Michigan, in Upper Michigan, at a KP index of about 5 or so, 5 to 6, you might see it in the Upper Peninsula. And down here, it needs to be at least a 7 to be able to see it in the lower parts of Michigan. So there's no forecast for anything that's strong. Now, if you're in the UP, you might get to see something tonight, but there's not enough down here to excite it all the way down here.
So Liam, I can add to that. There's also a magnetic measurement in addition to KP level.
Mm.
It's commonly called BZ.
Yeah.
I'm gonna look it up to see what it is, but I was able to photograph aurora from the thumb. It was in the distance. It wasn't overhead, but I was able to photograph it in the distance during spring equinox. And the value was southerly at 25. I'm gonna look that up because I think there's a combination. The KP level may have been 5 at that time, but the BZ level was also a negative. It was southerly at 25, and those factors combined to produce a pretty powerful invisible aurora from Point O'Bark Lighthouse, which is just right at the tip of the thumb of
Yeah, well,
Michigan.
you had the view over the water
There
as
are
well, which
some
means it's also
KP's a
unobscured.
factor. There's some other,
Yeah.
yeah, there are definitely
Yeah,
some
I think that's to
factors
do with the
there.
proton. I think the BZ is related to proton count, I think. And
Okay,
that would
that might
cause,
be,
yeah, and if the
that
proton count is
explains
high
it.
enough, then that could possibly cause it, yeah.
Yep. So yeah, there are a number of factors. So Eric, you're watching. We're looking them up in spaceweather.com. There's an app that you can get to look it up as well. The Space Weather app, and I think it's for both the Android and iPhone.
Yeah,
I see you left a message, Eric. I visit Whitefish Point in the UP for aurora viewing. That's absolutely perfect. Probably the best you can do is anywhere in the UP on the shore of Lake Superior. It's your best shot at seeing it when the space weather's good enough for it.
yeah. The best aurora I ever saw was in northern Sweden.
Uh-huh.
It was fantastic, and it was in their winter, so they get very little sunshine during their winter. But it was fantastic aurora up there. Yeah.
Yeah. Now the best that I saw, unfortunately, I wasn't into astronomy at the time, so I didn't have a camera, but it was right overhead in Madison, Wisconsin. It was I think we had a pretty major storm in the 90s, and the aurora was visible as far south as Detroit. And I was in Wisconsin at the time, and it was going over my head. Everything looked blue. Had I known what I know now about cameras and taking photos, it would have been some amazing pictures. I'm sure I would have caught all the other spectrums of light from that aurora. So,
and a lot of people
yeah.
don't realize the most common aurora is white. The reds, the greens, and the blues. The reds is harder to see. The blues and the greens happen more often, but the white is probably the most common, and it looks like cloud. I mean, unless you watch the movement of the cloud, you can't tell it's an aurora or not.
Hey guys, just a quick break. I have to break away for a minute. I have a plywood emergency that calls me away from my wife, so I'm going to let you go. You're in good hands with Liam and Tim and Awni, and I'll be back as soon as I can. Okay.
So, guys, as you can see, we got some clouds rolling in. So you can see some like cover, which is technically, all the details on the sun surface is getting demolished. So here you go, see? So I'll try my best to show you the prominence where, in my case, what I need to do is just pump up the exposure, and hopefully that will show something. Except with the cloud cover, it's kind of tricky. There. Yeah, we can see something here. Let me zoom in. There.
You must also remember we're just coming out of solar minimum. So the sun goes through 14-year cycles, and we're just coming out of the minimum, and we're starting to get active again. So in 4 or 5 years' time, we'll have a lawful lot to see on the sun as we approach maximum.
Oh yeah. There you go. See, so this prominence over here.
So you're saying now's the time for me to get that new solar scope, huh?
Good time to get one and get practice. Yes, yes, it is.
Yep, there you go. See this is the prominence. I had to pump up the exposure because the prominence is kind of very dim compared with the sun surface. But when I want to see the sunspot or the filament, it's technically covering up the sun brightness. So I don't need a lot of exposure here. So I can, drop the exposure down a little bit. And zoom up. That's technically what the sun surface looked like. The nice thing with solar imaging, basically, is because it's not like imaging the moon or the planets or nebulas or deep sky objects. The sun, what you see now, you won't see it in the next 30 minutes. It will change. Before I start this live session, look at all the texture. It's all gone now because of the thin cloud. Now we got like a very thin cloud, because otherwise it will look way much. The texture of the sun, it will look way much better now if it wasn't for the cloud cover. But for example, this sunspot, like I said, before I start the live session, I imaged that sunspot to create a time lapse later on, and I'll show you an example of the time lapse. And so back at 1 p.m. Oops, not this one. Actually, 12:30. This is how this sunspot looked like. Now again, you can't see anything. I need to pump up the exposure a little bit more. Yeah, see? So this filament is not there. It's gone. It moved. This one is still there. This one changed its shape from those two into like spread out. So that's the nice thing about the sun. It changes by the minute. And I'll show you same example, say an hour later. And there. I don't know if this is a good example or not. There you go. So this U-shaped filament now became like an arrow shape, and this like a, I don't know what you call it, like a flower shape or like a Y shape. Now it's spread out. Now it's like a V shape. That's what I mean. The nice thing with solar imaging is every day, it's a different thing, and that's technically what you like about solar imaging.
I've actually seen in the space of about 40 minutes where there was nothing, a tornado of plasma appeared, spun up, grew, and turned into an arc, into a filament, and then rained back down on top of the sun, all in the space of about 40 minutes.
Oh yeah.
So, Awni, we have
actually, speaking of,
keep going, Awni, and then I'll give you the question.
Speaking of which, I think just when was that? A couple of days ago, or not not very long ago. When was
I
that?
know what you're going to show them.
5 days ago.
Your tornado.
That was a twister. A solar prominence twister. You can see all the filament just like crawling in and out, trying to escape the sun's gravity. And this filament is actually rotating around itself. That's just crazy.
You know what that's called?
Now you won't be able to see that. I call it.
It's plasma indirection.
We called it solar tornado.
Or
they look like tornadoes.
Yep.
It's just crazy.
Quick note for you, Awni, from Jesse.
And that's what I mean by time lapse. This I'm sorry, what?
Yeah, quick question from Jesse Godsey. He says, Awni, your astrophotography seen lately is really great. Keep it up. Do you also do visual with an eyepiece, or are you all computer and monitor nowadays?
Oh, I do visual from time to time. Yeah, I do enjoy seeing, I do enjoy looking at stuff that I image and, kind of link them together. But yeah, I mean, for example, with the sun, you can do visual on the sun, visual visual astronomy. You can see all the prominences so easy because it's too bright, so bright. Um, Here's another, but yeah, let me just, yeah, there you go. This is, I guess this is my best time lapse of a filament. Um, and again, when I mean time lapse, it's not something that I captured, you know, in a minute or two. I usually capture a stream of video every 30 minutes, every 30 seconds for the next 2 hours. And then those videos, you technically, each video, you stack it together, you create just one image, and then you run those images in like 20 frames per second. And that's technically what you get. You get all the activity that is happening on the sun. You know, 2 or 3 hour activities in few seconds. How crazy is that? Now look at that.
You can imagine that granularity.
Can you post that link in chat?
Yeah, my
that Facebook link. Okay.
Oh yeah, yeah. You mean my Astrobin?
Yeah, that granularity you're looking at is like the surface of the sun. It's bubbling and boiling as it fuses the hydrogen to helium, and that's what you're seeing on the surface. So that's why it's constantly moving and changing.
Yeah, feel free to share this on YouTube if they like. There you go. And say, for example, this is not a time lapse, but it's just to tell you what crazy stuff you can expect from imaging the sun when you combine the filament with the prominence. Even though they're both the same, but because they're at the edge of the sun, you can see them more clearly, texture-wise. And as a filament, I mean, it's beautiful, but when it gets to the sun, actually this filament, I have the time lapse for that. This filament, when it was at the edge, it looked like that. That same filament.
Yeah, that's very cool. It's a huge filament. So how many Earths do you imagine would fit inside those huge filaments?
Oh, you can fit the Earth in this gap.
Yeah, the Earth is about the size of the pointer on the screen.
Yeah, you see that mouse pointer? You can fit the Earth in that gap easy. That's how crazy this filament, or the solar activities are. So
You must remember, like you can put 1.3 million Earths inside the sun, and still have room to switch them around.
I'm actually glad that you asked this question, Adrian, because I think I got something similar of what you're asking. There you go. Any second. There you go. See how big the Earth is compared with the
Perfect.
Prominence? That's just tiny. For those who ask, the sun is not black. It just masks the sun surface, the brightness, because this is just white. And it makes the filament more visible. It makes it more, you can see the texture much easier without having a bright white light masking it, or I don't know how to explain it. It's easier this way.
And for everyone who's there, who's watching, you can please feel free to ask questions. If you're on YouTube, type them. If you actually joined our link, and we'll answer your questions for you as much as we can.
Clouds are thinning, so yeah, we can see better textures now. Yeah, we still have small clouds, but
I always thought it was cool that in a close-up view of the sun or the moon, you see the clouds just sort of passing by it, but the light of the sun still shines through it.
Yeah, let me go back to the
Capture them and play those videos at you on Halloween. It makes it look really eerie when the cloud passes over the moon.
Very good point.
So if I rotate this, those two sunspots, which is on the right side, now it should be on the left side where from my imaging session. So we got a sunspot over here, this one, and we got actually two sunspots over here, which you can easily see. Those two, I think. And then if I go to the right, which is the left side of that website, there you go. We got one sunspot over here, and oops, wrong way. Let me dim down the exposure. Again, this is what's happening is the clouds are thinning, so I'm getting more exposure. There you go. Here's the other sunspot. And I don't know if you can see it because it's kind of zoomed out, but I can definitely zoom in and see if we can see something.
So while you're doing that, Awni, on YouTube, Jesse asked how much you have invested into your astrophotography equipment in total, but he warned you he's concerned, he says, or is your partner watching? My response is, I'm pretty sure your wife knows.
Well, I would say a lot, but
okay,
it would have been double that amount if I bought it new. So my advice to anyone who wants to get into astrophotography, let me put it this way, most astrophotographers and astronomers take really good care of their equipment, really good care. And when you buy a used equipment, you're not spending the whole amount of money. Like for example, this telescope, if I buy it brand new, it would cost me at least $2,500. But when I bought it for $1,400. That kind of saved me $1,000, $1,000. And look at the quality that I'm getting from it. It's a used equipment. So my advice to you, I mean, if you have the money, go for it. But if you don't buy new equipment, buy used equipment. You'll get the same quality. And again, like I said, most astronomers and astrophotographers take really good care of their equipment.
Yep.
And those that generally don't sell it because they know it won't be worth anything.
If it looks really, really low on price, then yeah, they haven't taken care of it or something's happened to it.
Yeah.
Look at that.
So I do have, if you want to see it, the telescope here at the observatory with a white light filter. This is actually not a typical white light filter. This is a Herschel wedge on the scope, but it's a white light. It's not hydrogen alpha if you want to see it.
Look at that. What's happening? Is this crazy?
Do you want to share? Do you want Tim to share his white light for a moment?
Yeah.
Share your screen, Tim.
I don't know if I can. No, it says I'm a lowly participant. I may not share.
Oh, you have to promote him, Awni. Or Jeff.
Oh, look at that. Now,
Jeff, I think, has stepped away.
Yeah, I think Adrian can
yeah,
do it.
Jeff stepped away. He'll be back.
No, Adrian's not a host. Adrian can't do it.
Oh,
Now, some might ask, why do I capture videos and and get an image out of that video? Why don't I just take a snapshot? Chicken done. The reason B is not all. I mean, now this thing is steady, but I don't know if you can see it or no. It's kind of wobbly, and the reason for that is the seeing. I mean, not just seeing clouds, transparency, heat, everything. It's there you go, clouds rolling in. All these factors will cause the image to not being sharp, to being wobbly. You don't have enough details within a single frame. So the technique that I'm doing, and most astrophotographers do, is I capture as many pictures as I can. In this case, a video. And when I captured 2,000 frames, now in hindsight, let me put it this way, at least 100 frame or 100 picture out of those 2,000 frame is where the image is the sharpest. And so the software that you stack here, those videos, technically pick those 100 frames and stack it together. So the final image out of the 2,000 frame video is the sharpest image, sharpest frames stacked together to create the best image. And that's basically the technique. The problem with that technique is you need tons of space, storage space, because each video is not less than 500 gigabyte or megabyte. I'm sorry, yeah, gigabyte actually. No, wait.
No, it's good. Yeah.
Gigabyte. So imagine if you capture 100 videos, 500 gigabyte each. We're talking about what? Terabytes.
Yep.
A lot of space. So that's another thing you need to invest if you're planning to do time lapses or solar imaging is storage space, a lot of it.
And fast storage. The faster the storage, the better. So solid state drives
you don't want
are better than a normal
that's
hard drive because you'll be able to store better. Yeah, SSDs is the way to go.
Yeah, now the clouds are not there. I mean, they're much better now. Let me see if we can see any.
Yeah, I mean, I'm checking the ASI. You use the same ASI 174 that I do, right?
Correct.
Yeah. So 2,000 frames, 4.71 gigabytes.
Yeah, but I crop it. I don't do full frame. Yeah, for example, yeah, this is, where is it? This is 540 by 480 pixels, and 2,000 frames is almost half terabyte.
So you're capturing region of interest.
Yeah, region. And the reason I do that is it will give me higher frame rate, like a 1 second exposure. You see, this will pump up to 14 frames per second. If I pick a smaller region of interest, which is technically what I'm looking for, look at that, 130 frames per second. It kind of it's gonna beat up the seeing if I do that. And in case if there is any fast move, any movement, I'll capture those 2,000 frames in what, 2 seconds?
Yeah, pretty fast. Yeah.
It's all about fast, being fast. But anyway, let's see if there's anything.
Yeah, you have to drop your exposure first.
Actually, let me pump up the exposure even more. Even more. Look at that. We got a prominence here. Let me zoom in a little bit. There. Oops. Sorry. Okay. Look at that. That's beautiful. Look at that prominence. Look at that prominence. It's trying to escape. But no. No one is escaping from the sun. Oops. Wrong way. See if we can capture more. Oops, wrong way. Yep, we got one here. We got another one here, and another one here. Pretty sure we'll find a huge one. Come on, there you go. That's the big guy. And when I mean the big guy, it's technically, I'm talking about this one, this tiny one.
Well, you can see that seeing conditions really wobbling. It's
Yeah, that's what I mean. Ooh,
through a bowl of water.
Look at that. We got a runner.
Yeah.
Look at that.
They're probably looping into that one.
Maybe
Yeah.
maybe that's what they mean by aurora activity coming soon. It's because of this guy. Look how big this thing is.
Yeah, possibly.
And it's
Yeah, but if it's not facing us,
But if it's no, but if it
doesn't
was
matter.
facing us when
It
it was
doesn't matter.
active,
okay. As
Doesn't
long as
matter
it
when
was
this
when it was
thing-
active.
when this thing
Yeah.
explodes, it explodes to every direction.
it
Yeah.
does. But if it's it depends. Like if it's coming towards us or starting to move away from us, and it gives off a CME, some of it can reach us. But if it's near the limb and spinning away, and it happens, the chance of anything hitting us is small because as I said, when it rotates, it leaves a trail of material in space, and that trail probably will not reach us. If it does, it will be the bare edge of it. So
Now, is it different on if it's rotating towards us? Is that like kind of throwing it at us then?
rotating towards us, it actually means it's not throwing it at us because it's pushing outwards, but the sun is rotating. So as anything pushed out and the sun's rotating, and the material has been pushed off, and it's been left as a trail behind the sun, not in front of it.
Not in front. Okay. So either way, it has
is
to
moving
be
away, so it leaves an arc of material trailing away from the sun as the sun rotates.
okay. So either way, it has to happen in a direction where some of it can get to us, and if it's aimed directly at us, then all of it gets to us.
Yeah, if it's aimed directly at us, and then the bulk of it reaches us, like we're in direct line of like directly in front of it when it happens. Because you must remember, most of these are in the northern or southern parts of the sun. So it actually, when it leaves the sun and branches out and spreads right over the distance. The 93 million miles it has to travel to reach us. So it does diffuse itself somewhat. But if it's a big enough one, then a large bulk of the material can reach us. If that happens, then the chance of aurora greatly increases, right? But the downside of that is if it's a big enough aurora, it can actually create enough charge in the atmosphere that it can actually take out the power grid and kill satellites and wipe out all communications. Because by ionize the atmosphere enough, if the particles enough, it will actually it'll be like an EMP. Well, it's not killing the electronics. They're shielded against that, but it does disrupt all their signals, and it could charge the power lines and actually blow transformers and take power lines, the power system.
There's the if you watch the animation, you can see it pop.
Well, Adrian, we got though this activity is rotating towards us.
Oh, that one down the bottom one
Yeah, but
popped towards us.
it's the one at the bottom around the, yeah, on the front of the disc around 7 o'clock there. You can watch it glow and sparkle as it pops out.
Yeah.
There you go.
So
That
that would be the reason then, yeah.
That was crazy.
Okay, yeah, I can see that.
Let me see if
So
I
that's the
can-
one that's headed in our
Hold on.
direction.
Let
Yeah.
me see if I can pause that. How do you pause? Oh, stop. There you go. Wait. Stop. Previous. There you go.
There it is.
Yeah.
Whoa.
Yeah. So that will now it's in the southern limb. It's in the southern half. So some of that will reach us because the surface is being curved. It's blowing this way. It's primarily blowing down at an angle, right? But
Again,
it
do you
is
need
spreading
tissue?
out. Some of it will reach us.
There's a box right here, there.
Hey, Amy, we can hear you if you're asking a question. Otherwise, if you go on mute.
Who was watching? My cousin.
Oh, keep
Yeah,
going, Awni.
The reason, the way I managed to see all the prominence activity over here is by pumping the exposure.
Yeah.
Now, if I drop the exposure to say, let's say 2 seconds and zoom out. And where is the mouse?
So you'll capture video with it overexposed like that, and then just bring in a disk and cover the sun, correct?
That is correct.
Hmm.
It's all in image processing.
Yeah.
So fun fact, Thomas Edison was up at one of the first solar observatories up at Lake Angeles. The astronomers showed him these glowing loops, and he asked them what they called them, and they said filaments, and he went, "That's a good name." And that is how that thing in the light bulb got its name.
Look at that. That's just crazy. Uh-oh. We have more clouds. But yeah, look at that ejection that just happened. Whoa, that's crazy.
So what
Well,
time
from
did
Seoul,
that
was
project?
it?
Does it say that projection? It says 9:24 UT.
So that only happened today. So that won't reach us for
Another 3 days.
depending on the power. It could reach us within anywhere from 1 to 3 days.
So when did that happen? That happened today. No, wait. Is that
So
in,
that could be UTC, right?
It is UTC,
UTC time? Probably UTC time.
So
Yeah, there it says there
We
UT.
are-
It says from Australia it was captured and the UT time was there.
that was
Hey,
roughly
UT.
noon our time, I think,
UT time
because
is
we're minus
4:50.
4.
So that
So
was
we're minus 4 in the Eastern Standard. So that would be noon 00 or 12.
That'd be-
No, that would be no, it would be midnight because 04. So
so
that would have
was
left midnight this morning, starting this morning.
yeah, that was
Basically,
what
12:50.
7, 10.
Yeah, it'd have been midnight our time by the time
that was like 15 hours ago.
yeah. Yeah, it was midnight, yeah.
Oops.
So the
Yeah, this thing was 15 hours ago.
so that could hit us within the next within 24 hours, potentially. It may cause aurora. Yeah.
It's my rotten luck. I won't be anywhere near, not even the thumb. I'm heading to Okie-Tech, so I'll be heading west and south. So I won't see any of it. I'll be looking for pictures online from everyone else still
Well,
in
it may not
Michigan.
reach us down here. It depends on the how big
How big
large
it
the
is.
atmosphere is.
Yeah.
Yeah.
I know the Aurora hunters will be out.
Speaking of what Tim can do or white light filter can do, I mean, even hydrogen alpha filter can be done. It can be done with hydrogen alpha filter. Is transits.
Oh, yeah.
The nice thing with solar imaging, I mean, there are many advantages in solar imaging. First of all, you don't need to drive to a dark site or dark spot or dark part, hours and hours and hours and in the middle of the night. You can do it from your backyard because obviously it doesn't matter. Second thing is you can do it in daylight. You don't have to, deprive yourself from sleeping. You can do it during the daytime. And a part of that, one of the things that you can image with solar imaging is ISS transit. For those who don't know what ISS means, it's the International Space Station. And sometimes, if you're lucky, the ISS will zip across the sun, and that usually creates a beautiful image, especially if you're capturing a video. Now I'm not lucky yet, but I did get this image from the internet somehow. Is it this one? Or maybe
I'll post something for you to share.
Liberty Mutual Insurance Company presents.
Someone's YouTube is playing.
Sorry to interrupt. Liberty Mutual customizes your car insurance, so you only pay for.
There we go. Sorry for that. I just posted a YouTube link there in the chat. Do you see it?
Hold on.
And that was me and John McGill capturing exactly what you're talking about, Awni.
Oh, woo, beauty. Let me zoom in.
Now, that whole thing, that clip animates in 8 seconds. In fact, it was actually 1.1 seconds in real time. So that's greatly slowed down.
Oh, come on. How do you loop? And let's make that HD. And zoom in. Look at that. That's exactly what I mean. Now, again, the difference between hydrogen alpha imaging and white light imaging is you won't see all these textures. You will see the sunspot. But look at that ISS.
So to do that, I went to transit-finder.com.
Yep.
And it said, if you stand on this spot on this day and time, you will see it happen. And that's
there you go.
How I knew where to go.
You can get an app for your phone. The Transit Finder is available on, I know it's on Android, I'm not sure about iPhone, but it's actually, you can get the app and it will tell you exactly where you need to be. And
or the website.
Timing down to the second about when it's approaching.
Yeah. So if you go to the website and enable your location through it, it will know where your location is and altitude and blah, blah, blah. And it will tell you all the transits, ISS transits, from this date to that date, and now it's pretty accurate. It's
you need to do it the day of, because even within an hour of it, you need to do it because the ISS orbit varies slightly, and
a little bit.
Yeah, but enough to say you're going to be on the center line or you're not going to be anywhere close, right? In the space of 2 days, you won't even be you won't be even in the same ballpark. So you need to do it the day of, and ideally within 20 minutes of actually, or maybe an hour or two of doing it, trying to image it to know exactly where to be. And then the timing, you need to have it real time on your phone watching it to be able to capture, because it'll vary so much. It's
it takes partial a second, like a blink of an eye for ISS to zip across the sun, or in this case, the moon. But anyway, what this website tells you is it will show you the moon transit and the sun transit, so solar transit. What you need to pay attention though is the altitude. You don't need anything below 40 degrees because that's going to be way too low, and the seeing in the atmosphere will affect everything. So if you need something sharp, you need something, anything above 40 degrees. And this will tell you all the transits within your location. For example, this is a sunset and it's 43 degree, which is promising, except it's not exactly where I am right now. But if you click the map, wait, how come you? Oh,
Got your wrong GPS location.
I guess I'm not auto detect. Okay. Come on, there you go. Now it's my location. And
well, now you have one.
look at that.
Tomorrow
That's
we have
5
a sun
degrees.
transit.
Yeah,
Oh, it's very low.
it's 5 degrees. It doesn't worth it. And this
Yeah,
one is at 30 degrees. It's kind of okay, kind of worth it.
There's a moon
Click
transit.
the map, and if you're not exactly in the middle, you can zoom. Oops. Come on. There you go. You can zoom in and you can find like a public.
Oh, this is really cool.
You've never used this before, Bob?
And you can find a
This is
public,
fantastic.
like a public, like a public park or
Yeah, we've done
somewhere
that.
that you can stay at, and it will tell you when, what day, what time, altitude.
Yeah, we've done
blah, blah,
that
blah,
as
and
a
it's
club
gonna go.
members.
Transit
We've done that.
duration 1.3 seconds.
Yeah,
That's exactly how it's gonna. That's exactly how long it will take for ISS to zip across the moon or the sun. 1.3 seconds.
So my learning experience.
So that's one thing.
My learning experience, so that you don't have to make the same mistake I did. I updated the data, and I did two mistakes. Number one, I did not generously buffer how many seconds before and after the predicted transit time I captured, and I did not update to the latest possible data. And it turned out it changed the transit by just a few seconds. And so I had two scopes set up, and one of them had the camera and the other one had an eyepiece. And the camera started, and then the camera stopped. And just at the moment when the camera stopped, in the other telescope, I watched the ISS go flying across in the eyepiece. So I missed it.
Oh yeah. You'll get that. You'll get that all the time. But yeah, you don't just get solar transit. You get moon transits. Like, for example, this guy is 56 degrees above the horizon, so it's really promising, and it's on Monday at 8 p.m. Is it? Yeah, 8 p.m. So
yeah, but you
before you go to bedtime, and except it's not exactly where I live, so I have to drive like, I don't know, 15 minutes. And again, you can plan it. You can find a park or somewhere, mall, anyway. Set up your scope, and it doesn't take all night to image it, just seconds. And again, this transit will only take 0.6 of a second.
You don't have to worry about fussing to get a perfect alignment of your telescope either.
Exactly. It's just like roughly aligned, and just, I guess 5 seconds, 10 seconds, 20 seconds before the transit, just start recording and wait.
Now, one other
hope for the best.
One other tip that I'll give is keep in mind to go around the Earth about every 90 minutes. The ISS moves about 25,000 feet every second. So if you were to take a frame rate of 1/1000th of a second on your camera shutter, the ISS will still move 25 feet in that amount of time. So you're going to get blurred solar panels. You're not going to get tack sharp. But the faster you can set your frame rate, the better you are.
Which means, so what Tim is trying to say is you need a fast camera, a fast frame camera to capture a decent, like the video that he posted, that's an insane fast camera. Wait, where is this? Maybe. Well, it's almost 4 months, so people are starting to run their YouTubes.
Yeah. I do a lot of streaming from at home, And the rule is you don't play online games when I'm streaming. Not allowed. Sorry, not going to happen. I have a standing rule, and they listen 99% of the time. They follow.
Well, I'm the gamer and the streamer, so
yeah. Well, I have kids, so they eat up all the time, and one of them's a teenager who loves being doing downloading.
But yeah, imagine this.
I wasn't paying attention.
You can turn the kitchen one off if you want.
So yeah, imagine if this transit takes a second from one edge to another, and
I forgot astronomy.
He's getting that slowness. He's technically capturing at least 120 seconds, 20 frame per second.
Oh, I think I was getting probably like 120, 130 frames a second at that time. Yeah.
Exactly. Yeah. This resolution is at least 120 frame per second camera, at least.
Yeah.
Yeah.
Because otherwise, if it's a slow camera, what you'll get is like tick, 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 tick,
you get blurred streaks.
Shots. Internet connection is unstable.
Did I hear somebody? Did somebody have a question? I thought I heard somebody trying to ask a question. Maybe not.
No, I think it's just Jim has joined us from University Lowbrow.
Okay.
We'll be seeing each other tomorrow. The adventure shall begin.
Yeah, across the great vaccine desert. Yes.
The great the
clouds gone.
Yeah, the vaccine desert. You're right.
Yeah,
the clouds are gone, Awni.
Chris Strang.
Yeah, it's a bit thinner. Yeah, the clouds are a bit thinner.
Chris Strang was just suggesting that we Photoshop
again because of that. I can see.
Go ahead, Tim.
I said Chris Strang was suggesting we just Photoshop the satellite map.
Good, but that's a lot of work.
I heard you said. Tim said Chris Strang suggests we Photoshop the satellite map. Now everyone knows.
Yeah, we can
what Tim was
Photoshop
trying
out
to
the
say.
clouds, can we?
I'm pretty sure that's possible.
They're doing solar observing right now.
Now I can't see the YouTube. Do we have any questions coming in there?
I can, and we don't have any questions yet.
Another thing you can do with solar imaging, except this one is not having a hydrogen alpha telescope. It won't help you. Is with the eclipse.
Oh, Jeff, while you're out
white light filter imaging.
Can you turn on the option that so you are gonna pick some of us that we can actually do screen sharing, like Tim Campbell and myself? And
I thought it was turned on. So yeah.
Yeah, please turn it on for us.
I thought we had.
No, Tim tried a while ago and he couldn't do it.
All participants. There we go.
Thank you.
Sorry about that.
All right.
That's a default at U of M. So
that's a default for me too.
I'll change that on the other things for tonight and tomorrow.
All right. Well, I will, if you would like. Let me do. That's the whole sun. Just tell it to do a region of interest and see if I can zoom in. And then I will hit the share button.
So what Tim is going to show white light using a Herschel wedge on the end of a scope.
So let me see if I can.
I gotta go look that up. I'll post it. I don't know what that is.
A Herschel wedge?
That's what I was thinking too.
Okay, a Herschel wedge is it's a diagonal that goes on the back of your scope, but instead of using a filter in the front of your telescope to filter the light, you allow all the light in, but the wedge in the back has built-in filters and has a radiator on the back to radiate out the heat, so it doesn't absorb and get super hot and burn.
Yeah, you can only use that with so much aperture.
Correct. I think it's 5 or
Yes.
6 inches. I think
It's
more.
it's 4 inches is mine. Yeah, basically a 100 millimeter aperture scope, and it goes on the back. So yes, so the full energy of the sun is piling through your scope, and that can do some serious damage if you put it on too large of a scope. But let me see if I can share the fire capture screen, and might need to tap the focus just a little bit. See if I can tweak that a little.
We do see your picture, Tim.
It's just a little sag in this.
That looks good.
Yeah.
Posted a link for a Lunt Herschel wedge. What kind do you have there, Tim? Look it up.
Mine is a Lunt white light.
Okay, I posted a link to a Lunt 2-inch solar wedge or
Yeah.
And you just put it on a refractor, but it needs to be small, or you get in trouble. So here are the sunspots. My camera is in north up orientation, except because it is going through a diagonal. Left is right and right is left. So basically, those sunspots are really on the other side of the sun.
That would be a good comparison to what you're shooting, Awni, because I think yours is right side up and everything correct, right? Or are you changing your view?
what happens if you hit flip X?
Oh, where do you see the flip X?
Over left, down about 3 inches from your cursor, underneath the histogram.
Underneath the histogram.
Down there.
Boom. There we go. All right.
Wow, look at that.
Slide it over.
Never mind. It's the sun as we see it.
There we go. Flip over to that side of the sun. So
the benefits of the white light over the HA is you see the sunspots and you don't see any of the granularity on it, whereas the HA gives you all the granularity. It gives you the prominences and all this kind of stuff, right? Whereas this only shows the sunspots, and they're darker spots, but they appear darker. That's because they're about 5,000 degrees cooler than the surface of the rest of the surface of the sun. So even though they're extremely hot, they're about 5,000 degrees cooler, so they show up dark.
Right, and so we've cut back the exposure of the camera to, for the disk of the sun, and that means that drop in temperature causes that much of a difference.
You see any plages, any lighter colored areas in this frequency? I can see them sometimes in my scope.
Yeah, I mean, I do see a little bit of the surface granulation coming out in this. Now you can see there's a cloud rolling in because it's not completely cloudless. But you can see a little bit of the surface granulation going on. When I looked through this with an eyepiece, it is spectacularly sharp. And that is what I like about it. But again, you can't use it on a very large scope. Because there is a diagonal, essentially it's a piece of glass, very barely silvered. So most of the energy shoots right through the glass and only a tiny bit reflects up. And the stuff that's going through the glass is landing on a heat sink. And then the stuff that's going up is going into your camera or eyepiece, because the way it works. But now, because you've bounced it off of a 45-degree mirror, you have effectively polarized the light. And that means that if you put a simple linear polarizer on the camera or on an eyepiece, you can simply rotate the eyepiece and the sun will get brighter or darker so as to make it much easier for your eye to see.
Yeah. Doug Box says looking good in the YouTube video. And he's joined us in Zoom.
All right, well, thank you. I'm going to go ahead and stop sharing because I think Awni's stuff is more exciting.
Yeah, I got one more question. What's the focal ratio of your telescope? Because I've read that fast scopes aren't too good to use with the Herschel wedge.
So in this observatory, this is an 80 millimeter, it's a Meade 80 millimeter triplet Apo F5.6. I'm sorry, no, F6.
Okay. Well, that's encouraging.
Yeah, that observatory is actually at the high school in Lincoln Park. They have an observatory in the high school, and the Ford Club manage the observatory for the school, and that's where Tim is right now.
So the focal length of that was 480 millimeters.
Okay. Because, yeah, I've read that they only take slow scopes, but I guess that isn't true.
Yeah, this was for the Aurora talk that many of you missed earlier. When it's a fairly high KP starting at 5, and other factors such as that BZ I was talking about are as low as 25 south, the display is pretty good. And this was from the thumb, shooting out north toward the horizon. This is just one of the images I was able to capture spring equinox. I was expecting a similar display for fall equinox, but we got a bunch of clouds, so I did not go out. So that's what you capture if the aurora is out. You can get it as far south as the thumb. If it's an even higher combination of factors, you get it you get it even further south. But I think what's heading towards us may well be visible. You may have to be further north in order to see it. And I think we're gonna know in a couple of days. Those of you that'll be in Michigan or further north, you'll know in a couple of days whether or not you're we have a good enough display to see as far south as the thumb.
Yeah, my phone will tell me if it's going to be visible or not.
Yeah. Eric Southerly has gotten it as far south as Silver Lake and Ludington. I'm not surprised. Here's Awni has a really good I think this is one of your time lapses of the aurora, right, Awni?
Yes.
Yeah, check that out.
From Rogers City.
Where Rogers City, isn't that on the other side of the bay near where is that, Awni?
It's east of the bridge
Okay.
on Lake Huron,
Okay.
on the tip of the mitten.
So it's much further north than I was.
Yeah.
At the tip of the thumb.
Rogers City. There, over here. So this is the thumb. I was here.
Yeah, we don't see any map.
We don't see anything on it.
When the
Now
there
we
it goes.
Yeah, that's the tip of the mitten, like they were saying. Thumbs further down.
So technically, I was looking towards the north. I was looking at nothing.
Yeah. See, I'm way down where you've got a couple. One of those spots down there, Point O'Bark Lighthouse, is actually shown, and that's where I was. Kind of it was a lucky guess because I was there to shoot Milky Way in, and I saw it in the distance, just like you've got it there. And I said, why not shoot a few pictures? So we don't know, those of you watching, we don't know if this is what you're going to see in 2 days. But if you do, it's spectacular, and definitely go out and watch it. To my understanding, you don't see the color as well with your naked eye. All of us who've seen it could vouch for that. You don't see it as the colors, but you see movement in the sky. You can sometimes see the pillars coming in and out. You can tell something's going on. And once you put your camera to it, all the colors show up.
Yeah, well, it helps a lot to be away from the city. I've seen the aurora from Ann Arbor, and that night it even beat the city lights. It was pretty amazing.
Yeah, I think Bob mentioned it. So you learn something every day. That's the beauty about this hobby. The flip Y and flip X now put the sun exactly like the Hydrogen Alpha website. And now I got this spot and this spot aligned with my imaging setup. There you go.
I'm just so glad that by the time the next solar eclipse comes around in 2024, the sun will be in its active stage again.
It should be pretty spectacular show, really.
Because the last for the last eclipse, the sun was really active. There was a beautiful, there was gigantic sunspots, and there was a whole array of them on the sun. And in 2024, we'll be well into it's 3 years time, and we're just coming out of the minimum right now. So we're going to be well into the active zone when that eclipse.
Yeah, the only problem is it's going to be
the cloudy season.
Yeah.
Well, who said there's no way I'm going to be in Michigan to watch that? We're already talking.
I think most of you will be in Texas to beat the weather.
Yeah,
I think I'll be the only one. Yeah, I'll be the only one staying behind and seeing what happens with family, because I did get a good view of it in Tennessee in 2017.
Yeah.
My son and my daughter have seen it, and I couldn't be more thrilled. The rest of the family's indifferent about it, but at least it would give them a chance to see it without. It's a chance, right? They'll experience it. If they can't see it, they'll experience how dark it gets during totality. So that's the rest of you. I'll have to depend on you to get the pictures and share the experiences, because I know most of you will go to Texas or somewhere further south, or maybe even west again to catch it.
Here's a question for you, Awni. The sun, I mean, it looks like it's overexposed in that upper left quadrant there. Is that, I guess, what's causing that? Is that camera setting, or is it?
No, just camera setting.
Okay.
Clouds were rolling in.
I was going to guess.
Clouds were rolling in, so I had to pump up the exposure.
I was going to guess that clouds were covering a part of the sun.
Sometimes I get those. Yeah, sometimes I get those sucker holes within the cloud, so the sun overexposed.
Yeah. Looks like I've got bad internet because I have to go without video in order to see everybody in real time. That's okay. They're here to see your face, Awni, not. They're here to see your face, Awni, not mine. So
it's not bad internet. It just people are coming back home and they're starting their streaming services.
Yeah. Yeah, Doug is. I heard you earlier, Doug. I see you're on.
Did that help your audio?
The stopping my video helped my audio.
No, I always have trouble with Zoom. I just restarted it and both my audio and video came on.
Okay. Well,
it didn't work before. That's all. Period.
Yeah.
And while I'm in Zoom meetings with the lowbrows, it restarts like 8 times in an hour. So I don't know why it happens for me.
Yeah, I've never had a problem.
No, I know most people don't, but I do.
Just lucky, I guess.
Yes, just lucky, I guess. That's one of the reasons I don't like Zoom.
You're the winner, Doug. The everyone else's problems ends up in your on your computer.
So I did a little solar stuff this morning, just for grins.
But yeah, now I intentionally overexpose the sun to see if there's any.
Well, we're curious of what you got, Doug.
And,
so we still see the prominences, but like the granularity's gone.
We still got this. But I see a new one over here coming up.
In my brief experience is like you either get the granularity of the surface or you get prominences, but rarely both of them in exceptional quality at the same time.
If the prominence is bright enough, if the prominence is bright enough for your angstrom tuning. Oh, look at that. Here's my tree. or if your angstrom tuning is good enough, you will be able to mix both of them.
Yeah.
You know, mix the prominence emission with the texture emission together in one frame.
It's all about tuning. It's all about tuning your echelon, right?
I mean,
Yep.
it's all about tuning. And here's an example of what I mean. Again, where is that? Hubble. Which one? There you go. This one. This was just.
It's not loaded yet. Give it a moment.
Yeah. So this was a time lapse that I captured of the solar texture, the sun's texture. But I guess my tuning was. I was able to get a prominence over here.
Where is the chart coming from? Okay. Somebody's phone. I muted the phone because there's a lot of background noise, like a radio or something coming over.
Yeah.
It sometimes happens.
Yeah, it does.
You guys hear me?
But yeah, those type of like, and what you apply the color, then you do that in Photoshop later on. Awni?
Yes, what?
Oh, I said to apply the color back to your black and white image, you use Photoshop.
Oh, yeah, I add that in Photoshop or PixInsight or anything. You know, any imaging software. You just play with curves and levels. Actually, speaking of which, I did add that in there. It's there you go.
Ooh, audio feedback from somewhere.
So
okay. Try again, Awni.
Yeah.
Okay. So can you hear me?
Yeah, I just
Yeah, we
muted
got
some others. I thought the audio was feeding back from them.
Okay, so the way you add color to like solar color to monochrome images is any editing software. Just change your midpoints through the levels. So just change the midpoints. The red midpoints to 1.6, green 1.6, and the blue to 0.2. And that will change a monochrome image to a color image. I can show you live if you want. Pretty easy. Now the way you apply it to every image, you just run it as a patch process.
Now it looks like Doug's having problems. He's going in and out again. Welcome back, Doug.
Reboot number 4.
Isn't this supposed to be third time lucky?
8th time lucky.
Here's an example. I happen to have a oops. There you go. Here's a monochrome image of that sun. What do you call it? The sun surface. And let's see. Nope, that's not one. There. You go to levels, and you of course you change that to RGB image, RGB color. Okay, black, and you go to levels, and you choose red. You change that to 1.6. You go to green, you change that to 0.6, and then you go to blue and you change that to 0.2. It's alive. You got color.
Da, 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 da.
3 small changes is all you needed.
Yeah. So now is the
Yeah,
the
and you can
idea
run
is
this as a path.
the idea is to change it to a color that looks
Go ahead,
natural.
Yeah.
Yeah, because I suppose I could go red 42, green of 7, and the other, I could blue whatever I want and end up with a psychedelic sun, but it won't look true to life.
Well, that's where the artistic side of astro imaging comes into play. Yeah, you can enhance or deviate the coloring as much as you want. Like the Awni just tweaked the colors there, and all he was doing is changing the levels around. But you can get real creative and go psychedelic, as you said, or you can slightly tweak it and make it look real.
Yeah. I imagine having something look real is more enjoyable to share than the sun and the sun in all sorts of colors.
Yeah, the natural look, what appears, what we believe to be a natural look, is easier for the eye to accept than it is to have something that looks all weird and discolored, because we look at it and kind of go, that's not real, that's definitely fake. But if you tweak it a little bit, it looks kind of real, and kind of like the color of the sun. People say, okay, right, now I get what's going on.
Yeah.
Well, none of it is any idea of what's true to life, but there are wavelengths that our eye will respond to better, and we'll see more contrast and more detail in the image by choosing the proper colors.
Yeah.
So the orange or yellow orange that Awni's been using does that, and that's why it looks so good, is because we can see more.
I posted a link in chat from the Solar Dynamics Observatory where they mix 3 different frequencies, and it is psychedelic, and you can get an example of what you're talking about there.
Yeah, this sun looks straight out of Star Trek right here. You see all of the various wavelengths coming off of the sun, but you're also not sure you're in the same solar system anymore.
That color's not right.
There you go. Now,
that's actually now yours looks
our
like a
sun was
close-up
a
of
cold
that
sun,
image.
cold star.
So, or you're taking in a different spectrum like calcium or sodium or things like that.
Yeah. Calcium Ks would give it a kind of a bluish tint. The sodium would be could be a white or yellowy white tint.
It's basically what what pleases your eyes.
Yeah, that's what I said. It's the artistic side of astrophotography that you bring out the detail that you like to see, what you would expect it to look like.
Right.
Like if you ramp up the red, it would just look
speaking
weird.
of details, now speaking of details, this is not something artificial. This is actually happened. One of the time lapses that I captured was that, and now, this will tell you. This explains why I masked the white light, because it's kind of more gentle to the eyes. And this video explains, it shows why I do that. But that's not what I'm trying to show here. I'm trying to show
bright light.
Something actually.
Now, boys and girls,
happened.
remember, never look at the sun.
Yes.
Yeah, should I
ever.
be doing the Astronomical League spiel? Please don't look at the sun without approved
Eye protection.
solar equipment.
Even with your naked eye, don't look at the sun.
Yeah.
And by the way, if anybody has solar eclipse glasses from the last solar eclipse, and you think, oh, I can look at the sun with this, no, they expire after 4 years. So what you have are out of date.
Give up, Tim? Is that somebody else's?
That's
I did not know that.
Yeah, they have if you look on them, they have an expiration date.
Oh
and they're out of
my!
date after 4 years. So
I'm posting that on Twitter. That's important.
the coding on that is actually bad. Go check the glasses you have. They have an expiration date.
So why is that?
The coating degrades.
Do not stare directly into sun with last remaining working eyeball.
So yeah, if you check the solar glass you have, the solar glass you have, there should be an expiry date on them, and if not, if you look it up, they will tell you that it's about 3 to 4 years, because the coating, because it's microscopic, it actually degrades over time. So anything from the last solar eclipse are no longer safe to be used. And even a white light filter for your telescope, for visual, you should replace it every couple of years because it does degrade.
Did not know that.
That's why we're here to learn, right?
Yes, we are. From our teacher, Liam.
I've been called many things, and that's not one of them.
So guys, the reason I want to show you. So the reason I want to show this is, who said the sun doesn't spread love? Look at that. It's a heart shape.
Someone's got a pop-up on your screen, Awni.
I think it
was Awni with a pop-up on your screen, yeah.
Yeah. I think we're waiting on it to show us the heart.
No, there it is. If you look at the shape, if you tilt your head to the left, you can see the bottom of it is the bottom of the heart.
Okay. Oh, okay. Yep, I see it now.
Yeah.
To me, it looks like a sock puppet, but
yeah, I'd go with sock puppet myself,
or maybe something else. But I mean, I see it.
It's a whatever they call those charts, charts or whatever. Where
Rorschach test.
There you go.
Yeah, Rorschach test, Jeff. That's
kind of looks like a cactus to me. So I've lived in Michigan all my life. Go figure.
No, if you tilt your head,
I'm sorry. It looks like a solar flare to me.
And put your index finger in the air and wave
Doug
your right
with the real answer here. Doug, it looks like a solar flare.
Man of great imagination. Yeah.
It couldn't be that.
Well, you're talking about great imaginations. If you look at the constellations, the guys who assign shapes to the asterisms or constellations in the night sky, those guys had amazing imagination.
No, they were on drugs.
Peyote.
Well, no, the Japanese saw the constellation and made it a logo for a car, so they made money off of it.
Yeah, Subaru. Yeah.
Yep.
That was the Pleiades.
Correct.
Yeah, and they didn't call it the Pleiades; they called it the Subaru instead.
Yeah.
I don't know if that's probably not a direct translation.
No, I'm not.
Yeah, Subaru has a different meaning. I'm sure I could try and look it up, but it's more fun to just say it.
I think it means Subaru means united.
Okay. I can believe that.
Yeah. And it is.
Let's move to do this. So now be good to go.
You have clouds.
Go. That is charging.
So, anyone have any questions about the sun or the science of the sun, of how it works, or?
Let me look back on YouTube, see if we get any.
Yeah, Liam. Here's
I've been
a
watching
question.
YouTube, so
Okay.
Yeah, both.
Here's a
I guess
question.
3 of us are.
Go on.
I
Someone's
will
asking a
need-
question.
Yeah, here's a question for you. Sunspot. Do you think? Do you reckon the dark spot, the black dot here,
Yeah.
is it more hotter?
No, It's
Cooler
about
Than the sun's
5,000
surface,
degrees.
or is it much cooler than the sun's surface?
It's much cooler.
Yeah, it's about 5,000 degrees cooler than the rest of the sun. And that's why it shows up dark in comparison.
Correct. It's just common sense. Brighter means hotter, darker means
yeah.
So the dark spots will
cooler.
still push the skin right off of your skeleton in a second.
Well,
Sorry, Tim, we can't hear you. You're not using your own. Tim, Tim, you're not using your own microphone. You're using Mr. Campbell's microphone, and you're so far we can't hear you.
Yeah, he's
Get closer to the laptop.
Dr. Day is explaining that it is still hot enough to instantly roast the skin right off of your bones.
But you have to get there first, and you'll probably be fried before you even get there. So.
Yeah, well, you know, the core is what, 15, 16 million degrees Kelvin.
Yeah.
Why?
Why? Heat and pressure, man.
Why?
Pressure.
No. Why is the most tenuous outer part of the sun's atmosphere but orders of magnitude hotter than the surface of the sun itself?
Well, no. So there's the core temperature, there's the surface temperature, and then there's the corona temperature. The corona is the hottest part.
Yeah. And we don't know, we don't really know the reasons why.
Actually, I shouldn't say it's the hottest part. It's hotter than the surface. It's not hotter than the core.
Yeah. And they don't really understand the reasons why they are. That's what they are researching it still today. You're muted.
I'm not.
I'm
I'm just distant.
He said that's what they all say. Yeah,
I'm typing all this in on the chat on YouTube.
So this is the temperature that once you get to that temperature, that roughly 15 million degrees plus, hydrogen atoms no longer bounce off of each other. They hit each other with such velocity that they smash each other, and you confuse them.
Are you saying that there's fusion taking place in the?
No, only in the core.
Yeah.
Actually, he is muted. He's coming through your microphone.
Yeah. They all hear you through my computer, Tim. They don't hear you through your computer. It's
testing.
Nope, it's still through his computer.
Yeah, it's yeah.
Make them muted.
So I think there's a problem between the keyboard and the seat cushion, Tim.
Yeah, that's an ID10T error.
Yeah. So what like the light now? What a lot of people don't realize is we see light from the sun, and like it takes 8.5 minutes for the light from the sun to reach us, right? But what the other thing that most people don't realize is even though the light is 8.5 minutes to reach us, it took 100,000 years before the light even got to the surface of the sun to leave the sun,
or more
to leave the surface of the sun to reach us.
That's an average.
An average 100,000 years, right? So when you see light coming from the sun, that was created over at least, or an average, over 100,000 years and plus 8.5 minutes ago, right? So the light is even ancient before it even gets to us, because the core of the sun is so dense that when in the moment that a light is created, a photon of light is created inside the core of the sun, it gets absorbed by another atom during the fusion, and then leaves again, and it takes what we call the drunken path. It bounces all over the place and hits every atom on its way until it reaches the surface, and eventually it leaves the sun, and then it takes 8.5 minutes to reach us from there.
Or random walk sometimes.
I call it the drunken walk is what I call it, because it's a short like someone drunk in the crowd.
Because you're Irish.
Because I'm Irish, yes it is.
So here's a question. Can you guys hear me?
Yes.
Here's a question for the grayer hairs on the club. If the sun emits light through fusion, you get 4 heliums and you get 4 hydrogens, you get a helium, proton, and some neutrons and some other garbage.
And a gamma ray.
And a gamma ray.
Gamma ray.
When the Big Bang occurred, there was no seeing past limit, the cosmic background wall, where suddenly the universe got cool enough that light was discoupled from atoms and was free to fly through space. And now we can look back to that point in time.
It was a plasma, and you cannot see through plasma. Yeah.
Right. So.
Very dense.
Similar idea to the fact that the photons are trapped inside of our sun, so they make
No.
it to the sun surface?
No, the reason is because the density of the hydrogen atoms and the helium atoms being manufactured are so close together that normally when that photon moving out as a gamma ray is emitted from one atom, instead of going in a gap between two other atoms, it almost immediately hits another atom and is reabsorbed.
There's no gap.
And then that one, well, there is a gap. It's just
It's
really,
too small.
really small. Yeah. And so the odds of it hitting a gap versus hitting another atom, it's going to hit another atom. And so it gets reabsorbed. And then when that one emits it, it emits it in a new random direction, which is why Liam calls it the drunken walk. But the thing is the farther you get from the center of the sun, the slightly larger these gaps become, which means that on average, the probability of it moving in a direction outward farther before it gets reabsorbed is better in that direction than it is going inward before it gets reabsorbed. And so it very, very slowly over time starts to make its way out. And the farther it makes its way out, the faster it can start moving. And so it's about 100,000 years on average, that's the estimate, before it reaches the surface.
So you're saying in the Big Bang, there were no such things as atoms, or plasma and plasma and atoms?
Well, at the Big Bang, it's believed that there were only bosons, only energy, no fermions.
Yeah.
So nothing that has mass, nothing that takes up space, only energy. And then the energy converts into matter, Higgs field, a la. And oh, by the way, if you listen to Roger Penrose, the universe was at maximum entropy when the event occurred. And it was the creation of the matter that caused the entropy to drop.
That means everything was equal
How
everywhere.
That which gave way to all the baryons, all the fermions in the universe weigh nothing.
Because you can turn energy into mass and mass into energy. Now you get a lot of energy, it becomes smaller.
Energy has no weight, no mass.
Does a photon have no mass? Correct. A photon is massless because nothing can travel at the speed of light if it has any mass at all.
But it has force.
It has energy, yeah.
Yeah.
F equals ma, I can make a little thing swing around inside a vacuum light bulb.
Well, it's also
F equals ma, where the m is a mass, and so there is no mass, right? So, but it has energy.
Well, what makes the little top spin inside the vacuum light bulb?
photonic pressure.
So that's actually believed not to be photonic pressure. They used to think that that's what it was. They now believe because that bulb, when they hit the black side, they said it gets hot.
It's propulsion.
And it's propulsion because the air pressure on the hot side is higher than the air pressure on the cold side.
Is that the Yarkovsky effect?
Yeah, it's radiating heat. Yeah.
The little radiometers that spin around.
Yeah, the same thing like that happened with the Pioneer spacecraft. When Pioneer spacecraft was traveling through space, they realized it was slowing down. And the way it's designed is on one side they had solar panels on the spacecraft, right? It was getting warm, and they had heat sinks on the other side. They radiate heat into the shadow side of the spacecraft. But what they found was the heat from the spacecraft was slowing down, and it shouldn't have been according to the way they were calculating. But because the radiator was on the sun, it was the opposite to the sun side, and it was radiating heat out into the dark side of space, away from the sun. That radiation was creating a propulsion and slowing the spacecraft down. It was minute,
physics,
but it was enough to slow it down.
Gentlemen, this is smart people talking smart physics.
I wouldn't go that far. I would say interested people. I would say more than anything else, but yeah. So the sun gives off light, and light has energy, and energy can be turned into. You can convert stuff from energy to matter and so on, right? But then that's why solar sails work, because photonic pressure, the energy from the sun can be converted into motion because it does apply pressure.
How long does it take a photon to go from a packet of energy to something with mass? What interval of time?
I don't think that wouldn't that depend on the matter, and wouldn't that depend on the process to do so?
Why wouldn't it be instant, or as opposed to it as the Planck constant?
Yeah, and I think you're now starting to ask about the Higgs field, and I don't know the physics of that well enough.
Yeah.
Other than the Higgs field is believed to be the process by which the energy will decay into a fermion and give rise to some sort of matter that takes up space.
Hmm. What was the guy that came up with the description of the Higgs field as the celebrity going into the room? What was his name?
Higgs.
No, it was a student that came up with the synopsis of the Higgs field and explained the Higgs field as, imagine a room, and the Higgs, just so people know, the Higgs field is what gives mass to matter, right?
Sure.
So, but the way he described it is, I think he won some award for this. The way he described it is, imagine a room filled with women, right? And they're all there to meet George Clooney, as an example. And so they're all sitting around these tables, and they're sitting at their tables, having some snacks or whatever it is, and they're all talking to each other, and that's fine. And George Clooney's not in the room yet, and a waiter goes in and out of the room, and he can go to the table and leave the room, and he will not interact with anybody, right? He just goes to the table, picks up his stuff, and walks out. He's a photon of light. He does not interact with anything in the room. Now, George Clooney walks into the room, and when he walks in, what's happening? What's going to happen? All of his fans are going to stand up and approach George. Now, as George walks through the room, and more of these people gather around him, his motion through space or through that room is going to slow down, and hence he's now gaining. So the people or the ladies in the room represent the Higgs field, and George Clooney is the matter that's been slowed down, being given mass by the Higgs field. But while that's still happening, the waiter can still go in and out because he doesn't interact with the people at all. So he's like a photon of light.
You still didn't quite answer my question.
We don't know the detailed physics of the Higgs to be able to answer your question.
I'll make it a little simpler. Imagine you've got a hydrogen atom. It's neutral. It's got one electron, one proton, and a photon comes along and hits that hydrogen atom, and it excites the electron up one level, and then that immediately drops back down and re-emits the photon. How long does that all take?
Oh, that's pretty much almost instantaneous, I believe. It doesn't retain it. I think it's virtually
nanoseconds, if that.
Oh, it's even less. It's probably
picoseconds
or even less. I would say it's almost an instantaneous reaction. It doesn't hold the energy. I don't believe. I think it's almost instantaneous. Would you agree, Tim?
I've got the Google. I'm going to look that up.
Look that up. Well, now here's the thing.
It'll come out as a different color if the conditions are right.
It'll come out as a different color if energy is lost. Yes.
Yeah.
If energy is lost. Yeah. But normally energy would not normally be lost. Certain types of things. So, for example, fluorescent material, where you've got the black light and you shine it on something, that is technically robbing some of the energy, emitting it as heat at a lower. So you're getting two photons out, right? One of them is at a very low wavelength, and then the other one is at a higher wavelength. You see the higher wavelength, you don't see the heat. So basically, one photon goes in, two photons come out. But if you add the two together, they add up to the same amount of energy as the one that went in. Yeah.
Well, you describe you're talking about phosphorescence, right? Or about the glow in the dark stuff, or are you talking about
fluorescence?
Oh, fluorescence is direct exchange, immediate exchange. Okay.
Phosphorescence is different. That's where the photon is trapped.
That's where the weird quantum effect comes into play. Okay.
Yeah, that's a weird effect. By the way, the other thing about the time, the reason that I couldn't even begin to imagine what the time would be is Heisenberg's uncertainty principle, right? So particle doesn't have a fixed location. It's a probability location.
Yeah.
So not only is it fuzzy with respect to space, it turns out new experiments show that it's actually fuzzy with respect to time. So
Sorry, we're nerding out and we're stealing on his thunder a little bit. Let's go back to solar observing.
I'm just enjoying. I'm just
having fun playing stump the panel. Come on, let's go.
enjoying the talk, and meanwhile, I'm doing something.
So Tim from Detroit, are you saying you already have the answer and you're just seeing if we know it?
No, I don't have the answer at all. I just figured this esteemed crowd might be able to satisfy my curiosity on a moment's notice.
Well, Bob and Google are covering for whatever we don't know.
I'm
So
looking.
we're
I
working
see a
on
lot
that.
of yes, it happens, but I'm not seeing a lot of how
Well,
fast it
we
happens.
may not even know the full physics about why it happens properly yet either. So
Yeah, I think you're getting into the realm of professional.
Prize for it. It's called the ultraviolet catastrophe. You solved it by doing.
Well, so we solve it with common sense type answers. If it happens and it doesn't burn my skin, then that's great. But professional astronomers are ready and waiting for you on YouTube to talk about those discussions.
My answer, which is guaranteed to be correct, by the way, is I do not know.
Yeah, that's most of our answers. But those are good. They are good questions. They provoke thought, and it's all stuff that's happening in the sun, so it does matter. It's
the first
it is
thing
relevant. So
yeah, the first view is always say if you to admit you don't know, but the second step is what I'd like to find out. That now you have an interest in science. If those two things happen in your head on a regular occasion, that means you want to actually go and find out. Now that's the process of science, right?
You know, the shortest possible time interval, time itself is also quantized.
Planck time.
Yeah. So the Planck time, the minimum Planck time, granularity for time is 10 to the negative 43 seconds. That's about as short as you can get. If you got something shorter than that, it can't be measured. Not with a photon, at least.
Yeah, well, maybe that's what's happening. We don't. I know I haven't researched it that deep. So most of the time when we do community outreach stuff and so on for astronomy, just explaining at that level that what's happening, that's mind blowing enough. You don't want to go into the in depth in math because a lot of people just get lost in there. So
yeah, at that point, math is the only way to explain it, and there's lots of good equations that we could find and then throw at you to say this is the answer, and it's this big old equation. So
when I got pages of text to get 50 pages to write out the equation on and make the calculations. So
when I got a line of 30 or 40 people in my telescope, the answer is I don't know. Let's go look it up tomorrow.
Yeah. And that's what
tomorrow. That's the key word. Tomorrow.
Yeah.
Not then, not on the tablet right now, but tomorrow.
Well, we'll give Bob something to do. So
I'm getting nowhere right now.
So there may not be an answer then yet.
Or it may be represented by a huge equation. How fast is that?
Well, the fact that I mean, the correct answer was I don't know, but we should have said that like 10 minutes ago because we haven't got the answer. We can't find the answer. We don't know the answer.
We can speculate about the answer, and that makes more great conversation.
Yeah, I understand that, but
someone might know the answer.
Well, someone might know, but we have discovered that we don't.
Kari.
So what have you been doing, Awni?
He's going through his
while enjoying your talk.
Yeah. Now that we fully hijacked your
some of the,
session, Awni.
I was capturing some of the sun's regions, interesting regions, basically just because I can. Okay. And because tomorrow's session would be nice to compare what happened 24 hours later, like
so
what changes happened. And but what interests me are two things actually. Those two sunspots, I can actually count 1, 2, 3, 4, 5, 6 spots, which is very interesting. That technically basically what I did in the beginning, captured the video and then stacked 20%, 20 best frames in that video and kind of sharpened that thing. So if you look at the original video.
I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in my image. Not counting those 2 that are outliers.
Like, oops, sorry. Like for example, the original video. I mean, the seeing is really good now, surprisingly. But the reason you capture and stack all these videos into the best, and you basically pick the best ones is to bring up all the details, better details, I would say, like there. So, I mean, if you compare this to that, it's a huge difference. And
yeah, I could see that. I could see the detail.
And again, I captured those 2 huge prominences. I would say like 5 minutes in between. Just
should I go home and come back with my
see what changes. Actually, bringing those to
solar.
No. What time was that? 20. So this was the earliest one. So let's copy this to and rename that.
This is interesting. So this is not rotated the way I thought it was.
01. Oops.
And
then this guy, copy paste, and 02. And if you see this, ooh. Yeah, you can see that. You can definitely see a huge difference in 5 minutes.
Yep.
It is crazy when you think about it. Just 5 minute difference and like things are changed. But anyway,
also brings some life.
It does. Totally agree. It does. And now back to the original subject. Oops, no. Yeah, I don't know if I can zoom that in. Control plus. Oh, there you go. Nope. Can't. Anyway, if I put the, nope, not this one. Okay. If I zoom this guy in.
That's a nice shot.
Yeah, look at that. It's just 2 spots here. If I count 1, 2,
I've got a shot from this morning as well.
3, 4, 5, 6 spots.
Yeah, we'll get Doug, we'll get your shot in here in a bit. I'd be curious to see what you got. But yeah,
It's just crazy. But anyway, for those who doesn't know how I do it, I use a program called AutoStacker. Mainly just load the image like so. Whatever I captured. Is this a good one? Ooh, that is a good one. Just load the image and choose the region of interest that I want the image to measure. Which frame are the best, and and analyze that. It will give me a curve. And by the way, you do that. I do the same process with lunar imaging and planetary everything. That anything that requires me to capture a video. So after analyzing it, it will give me a curve. These are the good frames frames, and these are the bad frames. So anything below 50%, I kind of ignore it. So this tells me 25% of my frames are good. So I'm going to capture only, I'm going to stack only 20% of it. I just need to put some points that the software will measure the good ones, like so. And sharpen those images as well. Multiplied by 2, sample it by 2, and then just stack it. It does all the things for me.
And it's free.
At the end, and it's free. That's the best part. And
keep in mind, those are files of 2,000 frames too. So it's chewing on quite a few frames.
Mm-hmm. So, yeah, that's not bad for an old laptop.
Well, I bet mine's older and slower.
Yeah.
Due to replace mine.
I need to replace my abacus.
I have a miniature tablet that has about as much power as a calculator.
Speaking of calculators and miniaturization.
Yeah, you can see the wobbly now, very easy. That's technically heat and seeing and transparency, all this crap. And we're done. That didn't take long. And the final image is, look
Dun, dun, dun.
at that. Ooh. There's definitely some eruption here.
And then Photoshop it.
That's cool. I can enhance it even more if I want to, but I mean, it looks decent.
Yeah, usually out of AutoStacker, it does a great job of cooking down the images, but you can often bring out even more contrast with either like Photoshop, or sometimes I'll use Registax with its wavelet features for some of the planetary stuff. And the detail is remarkable that it brings out. I've only had my H-alpha scope for a couple of weeks, so I can't really comment on how well some of those programs work.
But you're having fun the whole time away, right, Jeff?
Of course. I'm taking it on vacation with me next week.
Wavelets are black magic.
That's true, but they're very effective. They're magical.
Oh, interesting.
All right. Well, it looks like we still have 5 watching. Now, I don't know how many are on the Zoom at the same time as watching YouTube, but
let's just wrap things up by going through the sun right now and see what's happening. So we got a huge prominence at the top edge. Oops, wrong direction. That's a big one over here, and we got like a huge one over here. I don't think there's anything else left or happening. And let's see. Yeah, we got a tiny one. Yeah, prominence-wise, I don't think we have a lot. But flare-wise, I'm not flare, filament-wise, we got plenty. One there. That's a lot of filament here, and as well as yep, not a lot of difference.
I see a lot of detail.
from when we start the live session. But sometimes you get lucky and you get an eruption, and if you have the telescope running, you might be able to capture that. I guess the best part that we're looking forward to tomorrow, hopefully, if it's clear, is those sunspots, if anything changed. And I did capture, I did capture tons of those, and hopefully I'll be able to stack those and create a time lapse out of it before tomorrow's live session.
That would be cool.
2 hour, 2 hours of capturing what happened in those 2 hours. That would be nice. I bet a lot.
Yeah.
Yeah, with that said, I hope you guys enjoyed it. I'm just
Can I throw something up?
Oh, this was awesome. Thanks.
Happy that the weather is clear.
I say we let Doug throw something up, and then we let Bob throw something up, and then we call it.
Yeah.
Bob, I got nothing.
Yeah.
Go ahead, Doug.
Weather is not looking great. The forecast for tomorrow doesn't look fantastic.
Yeah.
Oops. Tomorrow's forecast.
It doesn't look great tomorrow afternoon, late afternoon or evening. In the afternoon,
Nope,
it's okay,
I don't
but by
see it,
evening, it's
Doug.
not looking great.
We see that you started sharing.
Yeah, I'm having problems again. Let me restart it.
Zoom is fun.
Yeah.
Send it to me, Doug, if you want to, on Facebook or whatever, and I will post it.
I'll be right back. It'll only take me a minute.
Okay. Looks like Tim has guests at the observatory. So, so the evening forecast is not looking fantastic for tomorrow tonight. So anyone who wants to see night sky stuff, tonight is going to definitely be the night for it.
Yeah, tonight is going to be good.
Okay, there we go. Now this should work.
Yeah, tonight is going to be decent. And tomorrow's
nice.
Tomorrow's iffy.
Solar imaging is also decent as well. So cool.
That was this morning with my 6-inch SET.
Whoa.
Yeah. Lots of sunspot and solar activity going on.
And it's only going to get better as the year goes on.
Yeah.
Okay, I posted a link in chat that shows a time lapse of from Soho showing the corona and the solar wind streaming out of it. Pretty cool.
Yeah, and people may not also realize that we get an aurora here, but you also get aurora on all the planets. That every planet has atmosphere. So Jupiter, Saturn, Mars. The further out the week it gets, but they do all experience aurora to some extent, and it's different colors based on their atmosphere.
Yeah, I'm looking at the Soho video. That's amazing. That's crazy, actually.
You should post it up so that show it on screen.
Let me share my screen again. Yeah. And go back to chat. Oh, come on, where's the chat? Oh, there you go. So, that's crazy.
Oh, that's a CME, yeah.
Over here.
Yeah.
Coming to a theater near you.
Yeah, so CMEs are really cool. Some of them are so big, you can you can like the trail they leave behind is amazing.
Yep.
Yeah, that link that's in the chat, that is current and it gets updated pretty frequently. So you can just continuously use that link and you'll see the sun for the last several hours.
Yeah.
Yeah, I bet that ejection is coming from. I'm not 100% sure though, but I bet it's coming from.
From the Soho.
Yeah.
Yeah, it is. A lot of our
So I bet
weather,
it's coming from this guy.
It could be, yeah. Or it could be no. It's probably coming from the sunspots. That's actually
because that's a lot of
facing
projection. That's true. That too.
Yeah, because we saw you showed earlier on. You saw that actually erupt. So that's probably what's emitting the particles that's actually reaching us because it's facing towards us. So the chances of that having an effect is greater, I'd say.
Yeah, I wouldn't know for sure, but when I see a prominence that big,
that might be interesting when it turns towards us. Because that's not turned. That's on. That's. Am I correct in saying that is approaching us now?
Look at that! Another ejection, another bright.
Yeah.
Spot. How does it mean?
That brightening just happened on that?
Yeah.
Yeah.
Wow.
That wasn't there.
Not even a half hour ago.
A couple of minutes ago.
Yeah.
Yeah. I see. Where is it? This one? There.
Very cool.
Yeah, that wasn't that bright. This part wasn't that bright. And look how bright it became. Now it's dimming. Look at that. It's dimming. It's just crazy. Matter of seconds. Cool.
Look at the power of the sun. It makes us mere mortals shake.
Yeah.
Or at least we stopped talking for a bit and just with our mouth open.
I got a question for everyone here. You're talking about all these photons going on the random walk, and that means that they're bunching up in the sun. Does that mean stars are photon capacitors? And if that's happening in a giant star and it goes supernova, that capacitor blows? And all the photons get released?
No.
No?
No, they're not capacitors because it's been emitted and absorbed, so they're being used in the reaction in the star. Now, really big stars, like in our sun, it uses the proton-proton chain reaction as well as how to create to convert hydrogen to helium. So 4 hydrogen atoms create helium. But in the case of really large stars, or way bigger than our stars, like Betelgeuse and all those others, they use a different. Well, they use some proton-proton chain, but they also primarily use a CNO cycle, the carbon nitrogen oxygen cycle, which is a totally different process. But it's not about storing them. They work their way through this. They work their way out of the star. It's just that they keep being absorbed and emitted, absorbed and emitted. So they're actually involved in the process by providing energy as part of the fueling of the process as well. So they're not being stored there. They're just taking their time to find their way out. And they help the overall process as it works, the overall nuclear fusion process. That make sense?
Yep. Got to wonder what the first scientist thought when he figured out what was going on, like looking at it going, oh my God, that works. Holy crap.
Yep.
That must have been a shock.
I think that accurately describes a lot of discoveries. Oh, wow, it worked. Time to write it down and put a paper in it.
Actually, I think a lot of discoveries come when they say, "Oh, I didn't expect that."
And
this.
I think the most common thing said in science, just like Doug said, is it did what?
Can we reproduce it?
And we
It
can
did
make it
it
happen
again.
again.
Because those are those,
Now we
yeah,
have
because those
working.
are those are the discoveries that they weren't even looking for. Those
Yeah.
are actual discoveries.
Yeah, very true.
There's a
Usually,
lot of
And
usually,
repeatable.
well, usually if it does what you expect it to do, it means that your hypothesis, you're already on that train to try to verify it and validate it. It's that surprise that is the actual discovery.
Yeah.
You know, when I see images like this that I'm looking at right here, I got to think that Carrington and that whole lot at that time would like kill to have seen images like this.
Oh,
You know,
yeah.
they didn't know any of this stuff was going on. I mean, this would have been amazing to them.
Like, if we went back in time with the technology we have today, like telescopes and so on, and you showed people what we can see
We'd
today,
be murdered.
We'd be burned at the stake,
you'd be
buddy.
black magic. You'd be deemed a witch.
Exactly.
What is this magic you're
You'll be a
showing us?
sorcerer,
It's either
magician.
it's either be deemed magic, and you'd be deemed a witch, or and be burned at the stake, or they'd make you the shaman for the village.
Yeah.
One or the other, because today's technology is miracles in the past, right? There's amazing stuff in the past. So,
Well, if considering even a solar eclipse was not very well understood, it just looked like something ate away at the sun, and then
that
out
was
of its
dark
mercy,
romance,
it gave
yeah.
it back.
Well,
Yeah,
that's
they
how
saw it as
shamans
dark
got
romance.
born. Those that had a little bit of math in their portfolio are the ones that took power because they could predict it.
Yeah.
Yeah.
Well, one of them died because he was off by a day. I thought there were two people that
China,
predicted the
wasn't it?
return of a comet. They were off by a day, so they were killed. It's pretty dangerous business trying to predict something and having one digit wrong in your calculation.
Wasn't that in
Oops,
China?
I should have carried the two.
Wasn't
Death.
it? I think that was in China, wasn't it?
I think it may have been in China.
One of the
I
Chinese
forget.
emperors, they were
Yeah,
predicting the return of a comet for him. Yeah.
Yeah, the emperor wanted to, I think the emperor wanted to show the people his powers, and he had the two astronomers with him at the time.
Yeah.
Tell me when this comet's coming back. There was a big party or something, and the comets didn't show up. The emperor goes, "What gives?" And I think they go and say, according to our calculations, I think we're a day off. And it was off with their heads. And I think the next day the comet did show up. I think that's how the story went.
Yeah, something along those lines. I remember that story. Yeah.
Yeah, that's when I learned.
Well, guys,
I don't want to be in the prediction business.
Well, I'm going to sign off, get something to eat before my my 6 o'clock, and I'll be on a
Sounds
little
like a
early
good
getting all
idea.
set up for it. And I will see all you guys later. This was
And,
really awesome.
Thanks.
Yeah, Bob.
Thank you all for
Yep.
joining. It was fun.
Yeah, and a great kickoff to the 25th anniversary of the Astronomy at the Beach.
Well
There
spoken.
you go.
Thank you,
We,
Ani.
Look forward for tomorrow. Hey,
Yeah.
pleasure.
I took notes.
Hopefully the sky is clear as well.
I sure hope so.
Cool. Well, then with that said, we'll see you guys tomorrow then.
Okay.
Have a
We
good one.
will end the stream and we'll end the meeting.
Bye-bye.